right, so the first thing you're going to have to do when you're in the lab, let's design our battery. We're going to put a beaker here. I have one beaker and I have a second beaker. In both of my beakers, I'm going to have a solution. So I'm choosing to use zinc sulfate, and that's aqueous. And then I'm also going to use copper sulfate. This is just in my example that I'm using. So in the beaker, if you look at aqueous ions, you're going to have zinc present, and you're also going to have SO4 -1, -2 present also. And you're going to have Cu2+, and you're also going to have SO4 -2 as well. But for the teaching purposes today, I don't want to crowd the information in the beaker. I want to be very specific to what we need to know to set up our electrochemical cell or battery. We also need a piece of metal. So I'll drop the piece of metal like this. And the metal, since it's zinc sulfate, needs to be a metal of zinc. So a piece of metal of zinc. If it's a piece of metal, the state of matter is solid. So I'll put an S there. And that's what this metal is. This metal is also called in electrochemistry terms called an electrode. So there's a vocab word there, electrode. That's what a metal is called. This metal is going to be a copper metal since we're using copper solution or copper aqueous form. So I have copper solid piece of metal. All right. I'm also going to have little alligator clips, the ones that clamp on here. I have another alligator clip, and that alligator clip is going to be connected to a piece of metal wire. Metal wire. So connected to this metal wire, I can have, let me just draw it out here since I don't have room with my words. I can have a box called a voltmeter, and I can measure the voltage from the flow of electrons. So I could actually measure the flow of electrons, how much voltage. If I connected, again, bear with me with my drawing here. This is a light bulb. And what would happen is if there's a flow of electrons, this light bulb would light up. Okay, so there's a couple options. I could actually connect to that wire, a light bulb, which we're not going to do. I'm going to connect it to a voltmeter so we can see the voltage and compare it to what the given values are. All right, so one last thing that we are going to have to add to this, because we're either going to have electrons flowing from zinc to copper or from copper to zinc. And we'll find out and figure out and determine which way they flow based off of information of reduction oxidation states and reduction oxidation equations, excuse me. We are also going to have a piece of cotton. And the reason I use cotton, there is another way you can use this. You could actually use make a bridge out of like rubber tubing and put the chemical inside the tubing and cap it with cotton caps. But what I have that's easy for us to use in lab is a sheet of cotton, and I'll cut them in strips. And what we'll do is we'll take each of those strips and we'll soak it in an ionic solution. So we'll soak it in an ionic solution. And an ionic solution is called a salt. So they call this a salt bridge. It bridges these two. Okay. Salt meaning not necessarily NaCl. It could be any ionic solution, but that's what a salt is. So they call this a salt bridge. So I'll just remind you that a salt is ionic. It's an aqueous form. And you know what? Let's use NaCl since we all think of salt when we think of the word salt bridge. But again, it's an ionic solution. I'm going to label this over here, salt bridge, just so we have it all labeled nicely and neatly. It basically completes the circuit and keeps each half reaction cell electrically neutral. Each half reaction cell electrically neutral. And we will talk about what happens there. I'm not going to go into a lot of detail at this level of what's happening molecularly down here, but we are going to see the big picture of it all. Okay, we're just going to be learning the basics because we're going to be building this battery and seeing the voltage and measuring the voltage as well. All right, so let's go forward. What information do we need to determine which way the electrons flow? First of all, we do need our reduction potential worksheet, and we need to find where zinc is. The zinc is down here. We need to write down that formula. And we also need to find where our copper 2, we're going to use copper 2 plus 2 negative electrons, and we need to write down that formula. So let's write down those two reduction oxidation reactions. So I have my zinc 2 plus, and it's aqueous, plus your 2 electrons, leads to zinc solid. The voltage here is negative 0.76, and I'll write that down. And then copper from our sheet is copper 2 plus, and that's aqueous, so I'll put the state of matter here, 2 electrons, and it goes to a solid. Its voltage is 0.34 volts, and that's all from that sheet that I gave you, the reduction sheet, nothing that you need to memorize. So here we have two reduction. However, in order for electrons to flow, one of them needs to be oxidation, and this is why we call it redox, reduction oxidation. We determine that based off of where they are. Which one is the more negative? Not necessarily which one is negative, which one's positive, but which one is more negative is going to be flipped and actually be the oxidation reaction. So when you're looking at the chart, zinc is more negative than copper. So we are going to take zinc and we are going to flip the reaction and write it as an oxidation reaction. So it's going to look like this. Flipped it around, and now we're left with zinc aqueous ions plus the 2 electrons. If we're flipping it because of oxidation, we also change the charge of the voltage, so now it goes to positive. I'll box that in just so we can focus on the actual reaction that it is. There we go. And I'm going to label this as oxidized. Right? And I'm going to put a Leo over here, just because that's an easy way to remember. Lose electrons were oxidized, which means this one is reduced. And I'm going to put a GR over here. Just remember, gaining electrons reduced. There's vocabulary that are associated with oxidized. So I'm going to rewrite the fact up here just so we can focus. These are our notes, but this is the image of what our battery looks like. So this is the oxidized, and this one is being reduced. When something is oxidized, it is called the anode, or the negative portion of the battery. So when you're looking at the battery, you can see that they're labeled positive and negative, and when you put it into, let's say, even our batteries that are here, there's an end that's positive and there's an end that's negative, and you need to put it in accordingly for the electrons to flow properly, for it to work. So the oxidized side and this side is going to be called an anode, and it's a negative. The reduced side is called a cathode, and it is the positive end of the battery. Again, we call it a cell, but for our purposes, we'll call this battery so we can visualize better. And since I put that information there, I'll put over here, it's the cathode, and it's the positive side. Now, something important that you need to remember from physics class that you may have not remembered, but that's okay, I'm here to tell you, that electrons flow from the anode, negative side, to the cathode, positive side. So I'm going to take my color marker and I'm going to show you. Let's see on this where we're going to flow. It flows from anode to cathode. So the electrons from this metal not the actual piece of metal zinc, but the electrons are moving in this direction from anode to cathode. So we show it on the metal where it's moving. Again, these are electrons moving. So we can show the flow of electrons. And this is the flow of the electrons. And it doesn't just stop there. There are some flows in the solution. Again, a little bit more detail, but I'm giving you the big picture of what we're seeing. All right, let's go further. So we now have half reactions of this circuit, or this battery rather. So let's put it into one redox reaction, a complete reduction oxidation reaction. In order to do so, we need to take a look at what we're given. So we are, let's focus, I'll color code this. This is yellow, I have yellow. So I'll color code this that I have on my left side of the equation, I have zinc. On the left side of the equation, I have copper. Since these are both 2 electrons, they're already balanced. I don't need to place any values in front to balance them. So I'm going to write zinc solid plus copper 2 aqueous. And they come from there. There we go. And then I'll just put my arrow and my zinc. Let me just kind of underline like that because I want to use my other colors for something else. So like that. So I have my zinc 2 plus aqueous plus my copper solid. All right. So my reduction oxidation reaction is now complete. This is the 2 half reactions that are within the 2, or both of them combined. Let me pause my recording just for a second. All right, so we have this redox reaction. Let's take a look at what happens to our ions. So we have a salt bridge. This is just part of the circuit. We have this salt bridge, and it's there to make it neutral, right? To help complete this entire electron flow. And what happens is that the negative portion, so Cl is negative, it goes, in the bridge, it moves. See, I'll go from here since that's where I drew it. It goes onto the negative side, right? To counteract it, to balance it. Let me use another color. Your positive portion, Na is +1, it goes to the side that's positive, your cathode side. So let me just color that so we know why it goes there. Let me color that here so we know this is negative, so we know where the salt bridge ions flow. Okay. What actually occurs is my electrons are moving into this direction. As they go into this direction, it's adding electrons to this metal. So it's not actually adding zinc metal to copper metal, the electrons are flowing. So because of that, you actually see or increase because of the electrons, you increase that metal. Well, if you're removing the electrons, what's happening to the zinc is I'll put a little chomp mark there, it's slowly becoming part of the solution. So zinc starts to just flake off as the electrons are moving right. As soon as there's enough flaking off, this is a battery that's not rechargeable. It's called the primary cell. So it's going to die and you're going to have to replace it. So this would be a battery that goes dead and you have to replace it. So this is what's occurring. Let me go back to the drawing board here. So I have my redox reaction, my long one, and then I have my shorthand. Let's take a look at my shorthand. Okay, so 2 half reactions put together. I can still make it even shorter than that. I can make it so it's focused on this battery or this cell. So the first thing I'm going to focus on is zinc. I start off with zinc solid, and zinc is oxidized, so I put a dash mark. And if it's oxidized, it's losing electrons, so it's becoming more positive. So it goes zinc solid to zinc aqueous. And then we have a second beaker. So the first beaker in shorthand terms is here. And we have a second beaker. And the way you designate the second side is you use a double dash line, just like that. So on the right side, we have copper. And it is gaining electrons and reduced. So if it's gaining electrons, it's going to be more positive. So then it goes into solid form. So this is the side that's gaining electrons. So this reduction oxidation entire reaction can be shorthanded to be looking like this. And then finally, we should be able to calculate your voltage. The voltage is 0.76 volts plus 0.34 volts. It's a plus because we flipped it. There we got one from there. We took both of them together and we get a spontaneous one, positive 1.1 voltage. And they refer to that as an E cell, sometimes looking like this.